Okay, let's resume. We talked about inverse trig functions in the first video, and we went through some examples of trigonometric equation in the second video. Third video will be a continuation of the second. We went through some quadratic or higher order trigonometric equations. We went through sine equation, we went through cosine equation, and then we went through an equation that we have both sine squared and cosine squared, but that one turned out to be a cosine equation. The reason that we can have a cosine equation for something like this is because sine squared and cosine squared are interchangeable by the Pythagorean identity. Cosine squared plus sine squared is equal to 1, or the formula number 1 in trigonometry in terms of the level of importance. Let's do a similar problem. Let's do problem D. And, well, I hope this time everybody can see this is a sine equation. Why? We have sine squared, we have cosine squared, but they're interchangeable as we can see over here. What's not interchangeable is the middle term, this one. I just highlighted the first order term, sine of x. That's because that term, the linear term, dictates whether it's sine equation or cosine equation. We can change sine squared into cosine squared. We can change cosine squared into sine squared, but just sine of x or just cosine of x stay the same. So the red one, the sine of x, dictates this is going to be a sine equation. So sine squared, that's okay. So this one is okay. Cosine squared, this needs some work. This cosine squared is the same as 1 minus sine squared. And we are in business. Everything is now sine. Sine squared, sine, another sine squared. This is a quadratic equation of a sine function. Let's algebraically manipulate by breaking out the parenthesis and moving 5 to the other side. Taking the like terms together, we get this quadratic trinomial equation. Leading coefficient is -3, so I don't like it. Multiply multiply -1 to everything. We have this simplified form, and then we can factor it. 3 sine of x plus 1 times sine of x minus 1 is equal to 0. From the first factor, we get sine of x equals to -1/3. That's a valid solution. Sine of x is equal to 1. That's also a valid solution. -1/3 is between -1 and +1. And 1 is, of course, 1, so it's okay. So we're going to get arc sine of -1/3 and arc sine of 1. After that, pi minus of those are also solutions. In short, we have something like this. Arc sine of -1/3 plus 2k pi. But if you use Mathematica or some computer algebra system, it'll say it's negative of arc sine of 1/3. Why? The reason is because sine function is odd function. So arc sine function is also odd function. So arc sine of -1/3 is same as negative of arc sine of 1/3. If you leave it as this, that's okay. The reason I did this simplification is because in case you use Wolfram Alpha or something to get a solution, this is what you're gonna get, and I don't want you to get confused. Okay, we have that, and then consequently pi minus of that is also a solution. So we have the second solution there. How about sine of x is equal to 1? Well, that's when x is 90 degrees, pi over 2. And pi minus of pi over 2 is also pi over 2. So that's when those pair of solutions collided each other. And here is the visualization. The red dot and green dot, represent the standard solutions, one given by arcsine, and then pi minus of that are represented as solid red dot and solid green dot, respectively. And when x equals a pi over 2, that's solid black dot here. Those solid dots are reproduced in the next period, and then the next period, and then the next period, and so on, as we move to the right. To the left, again, the same thing. So here's the visualization, and here's the whole solution. So I hope everybody feels okay about sine equations and cosine equations, even if you have to use this trigonometric identity, the Pythagorean identity, or formula number 1. Let's go over to a little bit harder problem this time. How about this one? 3 secant squared plus 2 tangent of x is equal to 7 plus tangent squared. In this case, what we do? Well, we just saw that sine and cosine, sine squared and cosine squared are interchangeable by this formula down there. And do recall that secant squared and tangent squared are interchangeable as well. We have this formula. One way to see this, well, we begin from Pythagorean identity, the original one, and then divide both of them by cosine squared. What do you have? Cosine squared over cosine, that's 1. And what do you have now? Sine squared over cosine squared, that's sine over cosine total quantity squared. That's tangent squared, the middle one. Third, 1 over cosine squared, that's 1 over cosine is secant, so this is secant squared. So we can actually derive the other Pythagorean identity from the standard one like this by dividing both of them by cosine squared. If you use that, then you can change the secant squared into, well, 1 plus tangent squared, and you're going to get only tangent. Specifically, we are talking about this conversion here. Secant squared in the first expression becomes 1 plus tangent squared in the second expression. And the second expression is just tangent equation, quadratic equation of tangent. So just break everything up, algebraically manipulate. Break up. Oh, wait a minute. This should be equality. Sorry about the typo. Okay. And then flip everything to the left-hand side and simplify. Excuse me, that was not equality. It was meant to be -7. We needed equals to 0. I apologize. This 7 is flipped over to the left-hand side. We have -7. This tangent squared is flipped over to the left-hand side, so negative tangent squared. And consequently, we have equal to 0. In the previous expression, I somehow missed that equal to 0 part. Equality is a verb in mathematical sentence in equations. So what I said early on without this equal to 0 part was incoherent expression, and I would have taken some points off if any of you did this, but sorry about that. Well, give me some credit, I corrected it now. Okay, let's go back and take the like terms together. We have something like this: 2 tangent squared plus 2 tangent minus 4. Can we factor this? Well, divide everything by 2 and make it simpler. tangent squared plus tangent minus 2. And let's factor it. This is modic, so it's easy factorization. Tangent minus 1 times tangent plus 2. So what do you get from the first factor? Tangent of x is 1. From the second factor, we get tangent x is negative 2. From the first factor, which is a standard angle, we get pi over 4. From the second one, we have arctangent of negative 2. By the way, how do you know that's pi over 4? Well, here it is. Trig diagram again. And when is the tangent equal to 1? That's when sine and cosine are the same. Pi over 4 and 5 pi over 4 in this case. Or pi over 4 plus pi, because pi is a period. So pi over 4, just find out 1, and then plus k pi. That'll take care of everything. The second one will be arctangent of negative 2, which we cannot find out precisely. So let's leave it at that, and plus k pi. Okay, so there are a little bit more advanced type of quadratic equations too, but in any case, please remember the Pythagorean identities. Cosine squared plus sine squared is equal to 1, and their variations. Let's see, do we have enough time to talk about the next one? Yeah, okay, I guess so. Cosine squared of x plus sine squared of x is equal to 1. Here, divide everything by sine squared. Divide this one again by sine squared of x. Oops. And then this one by sine squared of x. Okay, if I do that, what do you get? We have cosine of a sine. That's cotangent, isn't it? And we need to square it. Sine of a sine is 1, and 1 over sine is cosecant. So we have the other equality, the other Pythagorean identity, and it is possible to write trig equations with cotangent and cosecant squared. Personally, I have never used this one in trig equation problem. I usually stick to sine and cosine. I may end up using this in a little bit higher level problems, but most of the time sines and cosines are more important. Now, how much time do we have? Do we have enough time to start this one? Okay, let's go ahead and do that. This one is a little bit more challenging because this is quadratic. Cosine to the 4th power. How do we handle something like that? Well, here's the answer using Mathematica, and then here's the graph. We have how many solutions are there? We have many, 8 solutions between negative pi and positive pi. And do we have really 8? Between about negative 3 to positive 3. You can count 1, 2 from the left, 3, 4 in the left hand side of this y-axis, and then another 4. Yes, we have 8 solutions there. How to factor this? 4 cosine squared of x minus 3, 2 cosine squared of x minus 1 is equal to 0. If I remember correctly, this is going to be the factorization. Let's see, 4 times 8. Yes, I'm sure this is right. And then now what do you do? From the first factor, we get cosine squared of x is equals to 3/4. So if I take plus or minus square root, you're going to get cosine of x is plus or minus square root of 3/2. And square root of 3/2 is coming from the basic angle. So we have, well, some solutions. How about the next one? Cosine squared of x is 1/2. By taking plus or minus square root of x, we get plus or minus of square root, we have plus or minus 1 over square root of 2. And that's gonna give you some standard angles too. And the rest is left to the students.